Dear students, this is Dr. Bijwa here. In this video, we will solve a partial differential equation that is representing an heat equation. Okay. And in the last video, we have seen how to construct the equation of one-dimensional heat equation. Right? Now we are going to solve it. So this is the introduction. Consider a thin rod of length L with an infinite temperature f of x throughout and whose ends are held at temperature 0 for all time t. Ends are, so the boundary conditions are given here. 10 points when x equal to 0 and the u temperature is 0. When x is equal to L for any t, the temperature is 0, isn't it? And what else? Initial temperature. When t is 0, temperature is f of x, that is u of x equal to 0. So these two are boundary conditions, this one is initial condition. The rod shown in the figure satisfies the assumptions given in the page. So we have seen some assumptions of heat equation that satisfied for this given rod. So now the temperature u of x comma t in the rod is determined from the boundary value problem given here. This is the equation of the one-dimensional heat. Now we are going to solve this one as a boundary value problem for the given conditions. So the question is coming. So this is the given rod. In the beginning we are assuming u is 0, at the end is also u is 0. This is the rod given us. Okay. This first example we are going to solve the heat equation given here. K times uxx is equal to ut. This is nothing but k times dou square u over dou x square, which is equal to dou u over dou t for all x in the interval 0 to L and t is positive. Subject to the given condition, assume a rod of length L. See, boundary conditions. About the edges, the temperature is considered to be 0 and the initial temperature is given as a function of x, which is 1 for the first half of the rod, second half of the rod it is 0. See, and if it is the rod, total distance is L. For first half L over 2, the temperature is 1, initial temperature when time t is 0. Then here in the second part it is 0. So whatever the what we do, we have to remember this interval 0 to L over 2, the temperature is 1, and then rest of the part it will be 0 for the initial temperature, right? Fine. And let's start solving this problem on a different page. Solution is given here. Let's take actually a white page and then we'll solve it. Very big problem, so we need a lot of spaces. The problem, writing it again. K times u double x is equal to ut. This is the given problem. Boundary conditions. Boundary conditions are u of 0 comma t is 0 and u of capital L comma t is also 0. And the initial condition, initial temperature u of x comma 0 is 1 and 0 for the first interval, 0 lesser than x lesser than L over 2 and 0 for L over 2 lesser than x lesser than capital L. These are the given information. Okay, slightly bigger. Now let us start the solution. we let the solution u as the product of two functions x and y, where x is the function of x alone, y is the function of the variable y alone, isn't it? And we know what no, actually instead of y, this is from u. Here u is a function of x and t, so instead of y I would prefer to use t. U is product of x and t. Therefore, what is u x? Derivate with respect to x partially. So this is x prime t. Now what will be u x x? X and double prime t, isn't it? And what is u t when you differentiate with respect to t alone? You will find x remains constant, t prime, isn't it? So these are the information we get. Now we substitute all this in equation number 1. This is our equation. These are boundary conditions 1 and 2. This is initial condition, I see, isn't it? This is boundary conditions. Okay. Now equation number 1 gives what? Substitute these two. K times u double x, x double dash t, which is equal to ut, ut is x t prime. Now separate the variable. X double dash over x is equal to t prime over t times k. We will call it equal to negative lambda. We know the procedure, we have done this solving a partial differential equation by variable separable method. So now comparing the first and the last terms, what we get? Comparing first and the last, you will get x double dash is equal to minus lambda times x. That is x double dash plus lambda x is equal to 0. And now you should have another function. I will come to that point. Here comparing these two will be t dash is equal to minus lambda times t and k. That is t prime plus lambda t k. And the important point here is this is one equation of differential equation of first order. The solution of this one will be looking like t is equal to c times e power minus k lambda t. And the method has been already discussed, so I am not explaining this one. The solution, this one, we call it F. Now come to this one. Boundary condition 1. You should get some information from boundary condition 1. What is your boundary condition 1? U of 0, t is equal to 0, isn't it? Initial when x equal to 0, the initial temperature is 0 in the left end. But u of we know that u of this is x of x. U is xy. Our assumption is u is equal to x times t, isn't it? So x is a function of x and y, t is a function of small t, will be 0 when x is 0. So when x is 0, this is 0. So x of we don't know what x of t, isn't it? So x of x of 0 times t of t should be 0. No information about t of t. So obviously this will give x of 0 should be 0. From the boundary condition we are getting an initial condition for this equation. From boundary condition 1 gives x of 0 is 0. What is boundary? This is boundary condition 1. Boundary condition 2 gives u of L, t is 0. So x of L, t of t should be equal to 0. Therefore x of L is 0. This is our second initial condition we are getting for this problem. So this second order differential equation along with these two initial conditions will be called stum liable problem, isn't it? Check this one. This is for lower limit to 0. This is for upper limit L. No, this second order differential equation is in stum liable form. So we have to find the solution of this differential in three different cases. Lambda is negative, lambda is positive, lambda is 0. In all the cases we will club this t with x and write answer of u. Okay. And we will check which one will give a valid solution for this one. Okay, now let's move ahead. What is the first case? Case number 1, we will choose lambda is 0. Lambda is 0. What is the solution? So the differential equation becomes x double dash is 0. Therefore x dash is a constant. X is constant times x plus c. Let it be c1x c2. So now initial conditions we get here. This is another boundary, not initial condition, boundary condition for this stum level problem, isn't it? So x of 0 is 0 gives 0 is equal to c1 times 0 plus c2, which gives this for c2 is 0. Second, x of L is equal to 0 gives 0 is c1 times L plus c2 is already 0. This gives c1 is also 0. Therefore c1 and c2 both are 0. Therefore x is 0. Therefore u is x comma t, x and t. U will be 0 since whatever the value of t. Isn't u is 0. It's not a solution. Isn't it? Whatever the t. So when lambda is 0, the solution for the u for the original heat equation is 0. This is a trivial solution. This is not our solution. Isn't it? Trivial solution. So let's think of the second case. Lambda is negative. Now here I am writing now case 2, lambda is negative. So let us assume lambda is equal to negative mu square. And the procedure is already known to you. I think we have seen it many times in right from stum level problem. We are equipped with this one. So we will write the given differential equation as x double dash minus mu square into x is equal to 0. Therefore the solution of this kind of equation will be x is equal to c1 cosine mu x plus c2 sine mu x. Okay, no, this is not a complex roots. This is a real root case, so it will be different. What is it? C1 e raised to mu positive mu x and c2 e raised to negative mu x. You can write the auxiliary equation and find. This is the solution we are getting. Now again we have to find the values of c1 or c2 by using the boundary condition for x alone, isn't it? So boundary condition 1 gives what? X of 0 is 0. Substitute x equal to 0. Substitute x equal to 0 here. That will give us 0 is equal to x is 0, c1 plus c2 is equal to 0. Isn't the first case. Now boundary condition 2. X of L is equal to 0 gives 0 is c1 into e power mu L plus c2 into e power minus mu L. This can be written in the form, that is matrix form. 1, 1 the coefficient of c1 and c2, Here e raised to mu l, e raised to minus mu l. This is the first matrix, and C1, C2 second matrix is equal to 0. Here this determinant cannot be 0. Right. Since determinant of 1 1 e raised to mu l, e raised to minus mu l not equal to 0, we get C1 and C2 should be 0. The product of them is 0, so one of them should be 0. Therefore x is again 0. Therefore u, which is x times t, when x is 0, whatever the value of t, we don't need to check what is t. X is 0, so u is 0, not an eigenfunction, isn't it? Not an eigenfunction because it's 0. So only remaining case is lambda is positive. Let us try that as well. So case 3, lambda is positive. We will let lambda is mu square, isn't it? And then what we get from the given second order differential equation is x double dash plus mu square x is 0. So solution of this kind of problem will be x is equal to C1 cosine mu x plus C2 sine mu x. Now again boundary condition 1, x of 0 is 0, gives x equal to 0, left hand side is 0, so x equal to 0, cosine 0 is 1, so C1 sine 0 is 0, this part is 0, this gives C1 is 0. Let me check C2, x of L is 0, left hand side is 0, cosine C1 cosine mu L, but we know C1 is 0, so this time is 0, C2 sine mu L. So the first part of 0, what we get is C2 times sine mu L is 0. The product of them is 0. If C2 is non-zero, then certainly if you want a C2 non-zero, if you want to get a non-trivial solution, this part should be 0. Sine mu L should be 0. So, and we know that sine n pi is the sine. If sine is 0, then the theta should be n pi. Mu, therefore we will get mu L is equal to n times pi. Mu is equal to n pi over L. So what is our lambda? Lambda is mu square, which is n square pi square L square. This is the eigenvalue. For this eigenvalue, we will get eigenfunctions, isn't it? So what is your function final value f x? X is c, some constant c of c2 you can write, sine mu n pi x over L. This is an eigenfunction. Okay, now we are going to write the solution for u. Therefore, and the answer of t, what is t? In the beginning we have found t is equal to c, call it c3 e power minus k lambda t, isn't it? This was the initial solution for the t, and now this lambda will be replaced the value given here. The lambda value for this case, lambda is constant, e raised to k n square pi square over L square times t. This is t. So therefore the solution u is x times t. X is c2 sine n pi x over L, and this is c3 e raised to minus k n square pi square t over L square. This is not the final solution. There is a constant. We are going to remove all the constants. We have used only the boundary conditions. We never used the initial conditions. So again, we are generalizing this result. This is u. We write it un generalize. C2 and C3 we will write constant an. Okay. Instead of C2 and C3 we write nth constant for any. If n is equal to 1, you will first settle like this. Then it will be sin n pi x over L. This is the first term. Second term is e raised to minus k n square pi square t over L square. Remember, our C2 and C3 has been considered an, and now we have written this as general left function un. You can write un. Now, by superposition principle, you remember we have seen a superposition principle. It means if there are n solutions u1, if there are n solutions u1, u2, u3 up to un, then summation of all the summation of all this is also a solution. That's what our superposition principle, right? If all these are individual solutions, then sum of them, a linear combination of them will also be a solution. Let's take the combinations, all the constants as one. Then I am writing the general solution now. U of x comma t. This is the expected final solution, but not yet found. Summation un n from 1 to infinity larger, any numbers you can go. So this is summation n from 1 to infinity. What is un given here? An sin n pi x over L e raised to minus k n square pi square t over L square, isn't it? This is our u of x comma t. Now the initial condition. We have not used the initial condition. What is the initial condition? The initial condition given is u of x comma 0. When time t is 0, the function is either 1 or 0. When x lies in the interval L over 2, when x lies in the interval L over 2 to, isn't it? This is the initial condition given to us. So we are going to use this one in this equation. When you substitute at t is 0 in this equation, let this equation be equation number 1 or 2. Don't know, let it be 2. Using initial condition in equation number 2, what do you get? See, if you remove this, the value of an, you are done almost. We are going to work on it. So to find this an, I am substituting the t value 0 in this one. So x comma 0 will be summation n from 1 to infinity an. When t is 0, this term exponential e power 0 will be 1. So only sine will be there, sine n pi x over L, isn't it? Now which is looking like a half range sine series, which is a half range sine series of u of x comma 0. What is u of x comma 0? Which is given here. For this function, we find half range series, which is given here on the right side. Therefore, an is the bn in sine series, cosine, Fourier series, isn't it? Therefore, the formula for an, which is our bn in half range series, it is 2 over the interval of interval L, isn't it? And interval 0 to L, f of x sin n pi x over L dx by using Fourier series, right? Now what we need to, we don't need to integrate the function from 0 to L, because the function is 1 in the first interval, 0 in the second half. So f of x is nothing but u of x comma 0, isn't it? So what we find an is 2 over L, and integration from 0 to L over 2 function will be 1 in the interval. And now sin n pi x over L dx. So 2 over L is constant. When you integrate sin, it will be cosine minus n pi x over L divided by n pi over L from 0 to L over 2. So substitution of the upper and lower limit will get you this 2 over L. This can be written as L over n pi. The denominator can be taken outside, and now negative is also coming outside. In this cosine n pi L x should be replaced by L by 2. So what happens there? Upper limit cosine n pi x is L by 2 over L minus cosine 0 is 1. So here what we get further is 2 over n pi, and minus is multiplied inside 1 minus cosine n pi over 2. This L and L will be cancelled. It will be n pi over 2. This is our constant an in the given problem. So we are going to use the value of an in this equation number 2. Therefore we are done. Therefore the final answer I am writing here. Therefore the final solution of the one-dimensional heat equation u of x comma t is equal to summation n from 1 to infinity 2 over n pi. The constant 2 over pi can be written outside. I don't bother about it. Cosine n pi over 2 e raised to minus k n square pi square t over L square and sin n pi x over L. That is the end. This is the final solution. So what we are doing it one more time. Can you revise it? Let's go to the top. This is the problem, one-dimensional heat equation with the boundary conditions and the initial condition, isn't it? We first assume u is equal to x comma x times t, and then using variable separable method we are substituting the derivatives in this equation number 1, and then comparing the first and third term, then second and third term to get the differential equations. The first differential equation in x looks like a Sturm-Liouville problem along with the boundary conditions. From the boundary conditions we are finding the boundary conditions for so this one is x of 0 is x of L is 0, and somewhere it has been more. Okay, fine. What we are doing next is, now we are considering this term as a Sturm-Liouville problem and solving it for 3 different values of lambda, and check which one is an eigenfunction. After finding the right value of x, then we can think of t. T is one-dimensional first order differential equation t. So the answer is very trivial here. Now we will use this one at the end in u. U should be x times t. So x is valid for only lambda is lambda equal to 0 gives a trivial solution. Lambda is negative gives again trivial solution. So lambda is positive gives some eigenvalues lambdas for which there is an eigenfunction x, isn't it? So now we multiply the t value with x to write the function u, and we generalize the u using writing un, isn't it? And we write the solution u of x comma t by using the superposition principle. The sum of all un is again a solution, isn't it? And now there is a constant u an. This an can be removed by using the third condition, initial condition. When you apply x t is 0, this function, the equation, the solution that we are supposed to find becomes half range sine series or half range cosine series, depending upon the case, isn't it? Now we have to find this a1 by using Fourier series, Fourier sine coefficients, Fourier coefficient bn for the sine series. So we are finding the coefficient an and then using this equation number 2, that will conclude the problem, right? So we have used all the conditions, 2 boundary conditions, 1 initial condition, to write the final solution u of x comma t. This is the procedure, this is the common procedure for all the problems coming out in this case, right? If both are 2-dimensional cases, here in some problems we will find both x and t are 2-dimensional cases, second order differential equations. In that case, for both t and x, we should apply lambda is negative, lambda is positive, and lambda is 0. I think we have solved this kind of problems before. That's the end of this problem, and we will solve the wave equation in the next video. Thank you very much.